Hello, YouTube. So my name is Brian, and this is my first video. And today we're going to talk about something that has been weighing on my mind for like 5 years. 5 years of me just losing my mind. And so let's just get into it. Okay. There's the title screen for ya. Let's just get right into it. So what's been weighing on my mind for the last 5 years is this very equation that's right before us. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus ... Now, what does that ... mean? Well, it means that you just keep going, right? I mean, you just keep going until the end of time, I guess. You know, you just do all the natural numbers. You just sum them all up. 1 through infinity, you know? And one might assume, which, you're not wrong to assume, but most people assume that this is just infinity, right? Well, it turns out that it's not infinity, and this is where I lost my mind. It's actually negative 1/12. I know. I really want the viewer to just really take this in, really just stare at this for just, really the rest of your life, really, because this equation right here haunts me. And it should haunt you too, because how could it be that you sum all the numbers, all the counting numbers, and you get a negative fraction, negative 1/12? I mean, what in the holy heck is going on? And we're going to get into that today. This is a little more of an advanced presentation than you might be used to on the internet. I'll link the number file video that got me intrigued about this a couple of years ago. And go ahead and watch that first if you'd like. But if you'd like to continue down this rabbit hole with me, let's do it. This equation is, of course, related to the Zeta function, which is that thing that you see right up there. 1 to the exponent of negative s plus 2 to the exponent of negative s, and where s can be any complex number. And just making s equal to negative 1, you can see that you will get the equation in the middle, 1 plus 2 plus 3 plus 4, and so on, so on, so on. So today we're going to break this thing open and see what happens, okay? First, we're going to do a little review. So all you calculus students, get ready here. So here's the review. If you've taken calculus, you've probably seen this before, hopefully, because it's probably the most important function. You got the derivative with respect to x of e to the n x. So what is that? Let's just do this first equation over here. What would that be? Well, that's of course going to be n times e to the n x, right? The n just comes out. Pretty simple, right? Now, see this arrow over here? What if we said, well, okay, do that derivative and then say what happens when x is equal to 0? God damn it. Review. God damn. Okay. Sorry. I'm doing this on my cell phone. It's my first time. So what is that? Well, if we put an x over here, and then make that 0, well, then we're just left with n, right? And we can continue on Oh, there we go. Yeah, it looks like I was right. Good job, Brian. And we can continue on. Look at this. What if we did the second derivative? Well, the n squared pops out, and we're left with the original function, because that's the special ability of the exponential function, is that it's its own derivative. So it just makes it really nice. And, of course, if we let x equal to 0, then we are left with an n squared. Now, what if we have k be any number, any natural number, and we take the kth derivative? Well, an n to the k power pops out times the original exponential. And if we let x equal to 0, then we're, left with that n to the k. Pretty cool, huh? So here's where things get crazy, okay? This is where it gets crazy, and I want you guys just to stay on the crazy train with me. Things are going to get nuts. What if we, instead of saying k being an integer, we let it be any complex number? And that's including non-integer values, fractions and irrational numbers. What happens? Well, I don't know. I really don't know. I don't know what this s means when you have a complex irrational s. I don't know what happens to this differential operator. But just continue on with me down this rabbit hole. Let's just assume that n to the negative s pops out right here. And with its original exponential. And then if you let x equal to 0, then you're left with n to the negative s. Okay? Okay. Everyone just soak that in for a second. Just soak it in. Soak it in! And now we continue. Now we're going to sum this crazy derivative operator with exponential with x equaling 0 over n being the natural numbers. So we're going to have, you take every n to the s, remember from last time? And then you sum over n from 1 to infinity. See over here? Well, guess what? We're going to get the zeta function. Okay? This is the power of the diffintegral operator. Let's just go back here. What is the diffintegral operator? Well, it's really just the unification of derivatives and integrals and to non-integer value powers. I don't know. It's crazy, but it's gonna blow your mind what power it gives us when we use this and operate on this function here. So if you go to Wikipedia and you search up Cauchy's integral formula, you'll get this thing on the top here. The kth derivative of a function f at the number a, in green there, is equal, that's just another way of writing it, that, with this operator here. And it's going to be equal to this contour integral right here. There'll be future videos on this where we actually explore what is really going on here. Today, we're just going to take this as a truth, and we're not even going to do any integrals, really. We're not going to solve any integrals. We're just going to use the functional relations between f, k, a. If you put them all in this format right here, this diffintegral operator format, you get something like this. You get a factorial here over 2 pi I. I mean, really don't know what's going on, but we will later. Over the integral over some region C. A, of course, has to be in C. And, there's some other prereqs that need to go on with F. Has to be, analytic through C and blah, blah, blah. And you just get this integral. And what I've done is I was like, well, why don't I just put, down here a complex S in the diffintegral operator. And now we have a negative S, which is a complex number to the factorial. And everything else is the same, of course. So what happens? Well, you can't, if you have like a negative number, even a -1, you can't really take the factorial of a -1, let alone a fraction, but it turns out you can. As you can see right here, since z factorial is equal to the gamma function of 1 plus z, we can have a continuation to all numbers. I mean, the gamma function really can be evaluated at any number except the negative whole integers, and we'll get into that because some interesting things happen later. Probably in later videos we'll get into that. But for right now, this is our toolbox right now. We can write a function f evaluated at a with negative s derivative taken to it, the negative f. I don't know how to say this stuff, but you can see that if you want to take this derivative power of this derivative of this function and letting x equal a, you can get this. Okay, we just have that contour integral, and this is called the diffintegral operator. Okay, so let's just continue on. Sorry, it's my first video. Getting all jumbled up in my words here, so please bear with me. One more thing we have to review, and really these guys deserve a video by themselves, but there's these things called Bernoulli numbers. Bernoulli, I don't know how to say his name, sorry. And it's just a sequence of numbers starting at with 1, and then goes to -1/2, and then +1/6, and then 0, and then -1/30, and then 0, and then 1/42, and then 0. Looks like zeros on every other, value for k, because we're, k being the positive integers here. And how do you get these numbers? Well, you have this function down here, e or x over e to the x minus 1. If you take the Taylor series of that and do a bunch of derivatives, you get this Taylor series right here. And this can be written as this right here, where these Bernoulli numbers pop out, and you're left with x to the k, and then you can have this as k factorial, but I went ahead and did, jumped ahead a step, one little easy step, and made it a gamma function. So there you go. They deserve their own video because these things go real deep into number theory, and these, man, the Bernoulli numbers are crazy. They're very powerful stuff. So let's continue on. So now let's do the zeta function. Okay, zeta of s is equal to our diffintegral operator of the exponential function. We're taking the negative f s derivative of that, blah, 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 and using the formula from before, we can write this as a sum over the natural numbers of e to the n x, with x being down here, minus 0. So as you can see, I'm going to color coordinate these things for you to make it easier. The function that belongs in this bracket will be, orange, and you'll see why. Another thing to note is that there's a contour. This is called the Henkel Contour. It's a contour going around the positive real line, hugging it, not exactly on top of it, but getting as close to possible, going on the real line, going around infinity. So it kind of goes in this contour like this, counterclockwise, of course. And there we go. We'll get into that in a more later video to see really what happens there. So let's continue on. So now we have these three different forms of the zeta function. We have the series form. Now we have the diffintegral form. And now we have the Cauchy form, I call it. These things are all equivalent. Okay? All equivalent. Great stuff. Okay. So let's do some algebra. Okay? We're going to do some algebra. We're just going to do some simple algebra. We're not going to... What's so funny about this video is that we're not going to do a single complex integral, or we're not going to find any residues or anything like that. We're just going to do some simple algebra and maybe a derivative or two. And we're just going to look at the functional relationships between these three forms. Okay? This is why I love this representation of the zeta function, because you'll see the power of this differintegral operator here pretty soon. So let's go ahead and simplify this. We're probably going to take this down here. We're going to get rid of the 0. So yeah, let's go ahead and do that to get rid of that 0. Make that just an x to the 1 minus s up there. And then we're going to substitute x for negative x. And you'll see why in a second. So let's just do that. This is just simple, substitution rules for integrals. I'm hoping that this can be learned by any, calculus student, just first year calculus student. They can realize what I'm doing. Just treat this as a normal integral. Don't worry about the contour. We'll do that in a later video, because we're just going to do some simple stuff here. We're going to substitute for negative x, and then simplify. What happens is that, there was a negative x down here. We're going to pull that out, put it up here. And there was another one from, the dx, of course. There's a negative one that pops out. And so we're going to simplify more. And there we go. So we have this negative 1 to the s power, which is a crazy term by itself. That deserves a video all by itself. But now we have, this is what we have. And now, since x is in C of h, the Henkel contour, which is approximating the positive real numbers, okay, then e to the negative nx will always be less than 1 for every n and n, because they're being summed over the natural numbers over here, remember? And that means that we can use the geometric formula for a geometric series. You may remember this from calculus too, from calculus as well. You can take an infinite sum of geometric terms and, do that little magic. And so I can substitute that, as you'll see in the next slide here. Boom! We got rid of that summation term, and now we just replace that with this 1 over e to the x minus 1. Isn't that awesome? It's awesome. I love it. Now, next slide. We're going to multiply the top and bottom by x. Now, the reason why we're doing this is very simple. Really, it just makes the algebra easier for me. But really what we're doing is we're taking an x, we're borrowing an x from down here, and we're going to put it up top. And the reason why we're doing that is so that this term right here, this 1 over e to the x minus 1, will have an x on top. And those are the Bernoulli number generating function. So we will see here in the next slide. Yep, here we go. This is exactly what I'm talking about. Look at. We put the x down here, and then we put the x up here too. And now we can substitute this whole term here for this. Look at that. It's crazy. Let's just go ahead and do that. Wow. Now we're going to group all the terms. So what do I mean by grouping all the terms? So I replaced that generating function with the infinite series having the coefficients of the series being Bernoulli numbers over, the gamma function. But there's also this x to the k term. And guess what we can do with this x to the k term? We can just put it right down here. You see? We just put it right down here. And that's exactly what we did right there. Got rid of it. We can put the sum out here because now it's summing over everything. And so now we have this beautiful function of Bernoulli numbers, gamma function, -1 to the s, and then down here. And now what we want to do is we want to fix the index and put this thing back into Cauchy form. Excuse me. Oh my gosh, excuse me. So let's do that. To do that, we need to make up some terms here, change the coordinates or whatever you want to, whatever math terms you want to use in your head. See this right here? This is equal to 1 because the top and bottom are the same. But to be in Cauchy form, we need this exponent equaling over here. Remember, it has to be over here, here, and then in order to go back into this form. You'll see here in a second, sorry. So what I've done I moved the term over here. I moved that gamma 1 minus s back over into the orange zone or the function zone. Remember, we're just doing functional relations here. So I just kind of did some algebra magic. I just kind of moved things around. So now that we got everything's just all copacetic, we're back into the form. I added this green 0 here because you can just subtract to 0 because 0 is nothing, and now we're back in a Cauchy form, as you'll see here. Ooh, look at these arrows. So let's just go ahead and put this thing back into this. Watch this. Boom. Okay. Look at how crazy this is. Look how crazy this is. Okay. We didn't solve any integrals here. We didn't do any contour integrals. We didn't do any residues. We just did functional relations. Got everything just to be, copacetic with the indices and the exponents and the gammas and blah, blah, blah. And now we have, we did our algebra, and now we put it back into diffintegral form. And look at this. This is the most intriguing part. Do you see any x's up here? No. No, you don't. Okay, this is a constant function. Okay? That is something that, I really want you guys to all, just kind of think about for a while. Rewatch this video if you want, 1,000 times if you want, hopefully. And this is a constant function. And, I'm not going to claim that I know what happens when, you take a fractional derivative. But I do know that when you take an integer derivative of a constant function that's, an integer greater than 0, it's 0. So why don't we change our basis here? Instead of using s as any complex number, yes, get rid of all that. Instead of using s for any complex number, let's change our domain of discourse here to s equaling 1 minus n, where n could be any natural number. Okay? So this will, and change all the s's down here. As you can see, I did very beautifully, blah, blah, blah. This thing will, if you say, what is zeta of negative 2, you would put n as equal to 3. 1 minus 3 is equal to negative 2. And then all these things down here have been changed. And then we go in the next slide here. And we do some simplifications, as you can see. And this thing is beautiful. And this is what we all have to kind of think about, kind of step back for a second and look at this. Like I said before, this orange thing, whatever it is, it's a bunch of nonsense, that's for sure. Has Bernoulli numbers and blah, 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 gamma functions. I don't know what's going on. But I do know that there's no x's in it. So it's a constant function. And this thing is taking k starting at 0, and it's going to go where n starts at 1. So it's going to go through all the powers of the derivative. And every single one will be 0 except when n is equal to k. And that's the big aha moment, you might say. We want to figure out when n is equal to k, everything really just simplifies really fast, collapses on itself. Look at this thing. What is the zero derivative of any function? Well, it's just itself, right? Because you're not taking the derivative anymore. It just kind of disappears. And now we're left with this. And yeah, as you can see, it just pops right out. Look at that. This zeta function of 1 minus n is equal to this. Okay? And I brought that to the next page here. We can make our lives easier and change, the index to be more agreeable instead of the natural numbers, and you have to using this 1 minus n nonsense. We can just make the transformation of n going to n plus 1, where we have access to 0, 1, 2, 3, blah, blah, blah. So the zeta function at all the negative integers, including 0, is equal to this. The negative 1 to the negative n power times the Bernoulli n plus 1 number over n plus 1. And you all were also probably trying to figure out where all those gamma functions went. If you know the relation between the factorial and the gamma function, you'll see, and when you type in n is equal to k, you'll see some great cancellations. I mean, look at this. Gamma n over gamma n plus 1 is just equal to n, right? And then this is just 1. So that's just 1. So a lot of beautiful cancellations happen. And blah, 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 blah. And now we're just at the punchline here. The function or the formula that we just found. And now if we inputted -1, we get this, -1 over 12. Wow. I mean, it's just crazy. It's crazy to me that this works. I think what this presentation kind of shows is the power of this operator that we discovered, this fractional derivative operator. And, we got to the big punchline here. 1 plus 2 plus 3 plus 4, ... is equal to -112. So now what? This is my first video. There's a lot to take in, I know. Hopefully my future videos will be more concise, focusing on more of one subject. And a future video is using this this diffintegral operator for the representation of the zeta function, and finding the residues of it, not restricting your domain of discourse to just integer values for s, but for any s. And you can fish out some residues and you can get the functional equation. And that's a future video. In that video, it'll be a lot harder to go through because you actually have to do some residue analysis. But it's very fascinating. You'll actually get to see the machinery that this operator holds inside of it. And that will be a future video. Don't worry, more is coming. So this is what I really wanted the internet to really take in. This fractional derivative operator, this is analytic continuation. I've been, doing this zeta function stuff for 2 years, 3 years now, really hardcore. And one of the problems that I was, coming to is, all these mathematicians were just kind of pulling formulas out of nowhere. And, if you're looking at, I started with, Riemann's paper on this subject, and he just seems to come with these formulas out of nowhere, these contour integrals and blah, blah, blah. And, analytic continuation was mentioned, and I didn't really understand what it was until I figured out what a fractional derivative was. Because that is analytic continuation. That is how you break open numbers. Okay? It gives you a lot of power. There'll be videos in the future where we will really look into this and figure out what I mean by breaking open numbers. But yeah, also I know that there's a functional analysis representation of this, and this operator has a spectrum, and we will get to that in future videos too. There's 100 videos I can make out of this, okay? And I have done years of work, a couple years of work, hardcore. I want to get this out to YouTube. I want everyone to learn this, and please comment on my videos if you see any mistakes, or new ideas or whatever. New ways to think about this, because I'm learning too. I am learning too. I still don't know what's going on. I know I've fell down this rabbit hole, and now we're really getting into what I call the personality of the numbers themselves. And here's some little formulas I've maybe a little foreshadowing for future videos. This kind of goes more along the functional analysis route. You can get the resolution of identity here. Okay, this is just 1 over here. Everyone just stop and think, like 1 to any power is just 1, but I can really just manipulate that and find its resolution. You can resolve it to any basis that you want, and we'll see that in the future. And also, we know that the zeta function has a deep connection to the prime numbers. As you can see here, this is the diffintegral representation of the zeta function, with prime numbers being the main event here, as you can see by my red little P. And that's, pretty crazy stuff. So that's it. If you want to shoot me a tip on PayPal or support me on Patreon, you can. Not really required, but I really appreciate it. Help me get more of these videos out. And yeah, that's it. And please comment below. Please subscribe. Please share. This is my first video. Hopefully my presentation skills will get better. They hopefully will. And I'm still learning how to video edit, blah, blah, blah. And so I really am jealous of people's skills on the internet. I wish I had their computer graphic skills. 3 brown, 1 blue is an example of that. I really am jealous of your skills. But anyways, that's it. This is Brian signing off.